analysis, the easiest way, not the easiest, the usual way to analyze data, historical data, and to quantify impacts and to be able to predict into the future is trend assessment. This is much used in climate change, but also you can use it for land use change. Like, what is the effect of land use on water resources? You may relate land use, historical data of land use, to historical data of water resources and seek a connection. Trend assessment. Trend assessment it looks like very simple because you know already how trend is estimated. The easiest way to estimate a trend is linear regression. So, trend assessment linear regression. Like, let's suppose that you have water resources, Qt, with respect to time. You know that you accept that there is climate change, and you look at historical data and you see something like this. Clearly there is a trend, an increasing trend. The trend may be decreasing, and how to estimate it and how to project it into the future. The most used way is linear regression, and then I can project it into the future. Why is linear regression used instead of polynomial regression, for instance? The answer is very simple. For reducing uncertainty, a striking feature of linear regression is limited uncertainty. You can call it also robustness. The method is robust, and it's intuitive what it means. Robust. And you know how to estimate a trend in linear regression. I put it, the formula here. I put it here. I'm sure that in some of your previous courses you studied linear regression, and it's very simple. Linear interpolation, you can call it. You fit a straight line to data. Let's call the data yt. You fit a straight line, which means an intercept at time 0 plus a slope b that multiplies time plus a residual, an error. Okay, so this is a formula of a straight line with two parameters, a and b, that need to be estimated. The intercept a, which is here, this is a, and the slope b. The slope b is the tangent of the angle that I indicated here. So b is not the angle, it's the tangent of this angle, tangent of the slope. Oh, sorry, tangent of the angle. Okay, so you know how to estimate linear regression. I will say something more about it, but we don't go into the details of the estimation of linear regression. I just want to tell you that usually it's estimated, the parameters a and b are estimated by minimizing the sum of squares, and you know it. You know already what sum of squares means, because we discussed it already. Now, while it's very clear what is a trend, and it's even more clear what is a linear regression. Linear regression is mathematically defined. What is a trend? I may ask you this question. Can you please give me a definition of what is a trend? We can easily define what is the slope of the linear regression and what is a linear regression. This is easy to define. But what is a trend? And we have clear what is a trend. No? It's a tendency. It's clear. No? We often use this word. There is a trend today, there is a tendency today to prefer fried food. There is a tendency today to vote for the right, for the left. It's clear, there is a trend. But what is a trend, if I had to define in mathematical terms? And it was interesting, one day I went to a conference and there was a famous statistician and she said, I'm repeatedly asked to define a trend, and I browsed in the web, in the textbooks, and I couldn't find a definition for a trend. So she said, my conclusion is, but it was not her conclusion. She quoted another researcher, and she said, I'm quoting from this other researcher, and give this definition. A trend is a trend, is a trend, is a trend. And I liked it a lot, because it implies that we know what is, but it's not mathematically defined. And why is this question so important? Because you may think, why Montanari is insisting on that? Because to identify this trend is something that may quickly revert. If you add more observation into the future, it may go like this. Again increasing and then decreasing again. So, is this an increasing tendency or just part of a cycle? This is impossible to say. When you talk about a sample of data, and this sample is, of course, limited, because it's impossible to cover the full extension of the processes we are interested in. This sample of data, for sure, if you estimate a linear regression, it does not slope zero. It's never flat, the linear regression. It's either increasing or decreasing because of the uncertainties. And then, could we distinguish something that is going to increase forever from something that is increasing here, but maybe decreasing later? And if I go, for instance, a very good example is the picture that I already showed you about the Po River. And if I get into, I think it's already here, just one second, yeah, it's here. On the lecture, you see this is the mean flow of the Po River. So you estimate a linear regression over a window that is moving, and you see that sometimes the linear regression is decreasing, increasing, so what is a trend? This is something that you can say here there is a trend in the far past, but then in the future, in the second part of the series, the trend is reverted, so it's not a trend, it's just a part of a cycle. But anyway, this historical data analysis is the way, is one possible way to go and to project into the future. And there is to say that the good thing is that the linear regression is quite robust. If you use the polynomial regression, you may get like an explosion, an exponential tendency, which is, given the uncertainty, is not advisable. This is the mean of the sum of squares. And there is a discussion in my webpage about how to discriminate between a positive slope or a negative slope, which means positive or negative b values, how to distinguish from the zero value for b, basing on statistical analysis. There are statistical tests that allow you to say if this regression line is indeed with a slope different from zero, or we cannot reject the fact that the slope may be zero. There is a discussion on the web pages. Usually I'm not interested in that at the exam. And so let's take that I'm not interested in that, okay? And I just, in fact, it's not reported here. And then there is modeling. Modeling, which we already discussed. It means that you try to, sorry if it's written in a small character here, but I can summarize the content of this slide very easily by saying that you know that natural processes and human processes can be described by models. We considered, for instance, rainfall and off models. And we know for some of these processes how to build a model, like a rainfall and off model, we know how to build it. For other processes, we didn't discuss here possible models, but you can always identify a model for describing a physical process. There are two, we can split models for assessing human impact in two categories. And the first category, which is discussed here in the web pages, is models that consider human impact as an external driver. Like, I estimate water resources availability in a river in pristine conditions, no humans. Then I know that there is a water withdrawal, I subtract it. So the human impact, which is water withdrawal, is an external driver of the system, of my model. Is an exogenous component of my model. So again, the model is in pristine conditions, no humans, like a rainfall runoff model with no humans in. And then the human impact, I quantify it independently and I subtract it. Again, the example of river flow minus water diversion is an excellent example. What is the second category of models? The second category of models is given by the models who consider humans as part of the model, not an exogenous component, part of the model. What is the difference? The difference is that you can take into account feedbacks. So, I go to the previous example. Previous example, you study river flow in pristine condition and then you subtract water withdrawal. But what is the purpose of the withdrawal? The purpose of the withdrawal may be irrigation. If you irrigate, you increase evaporation. If you increase evaporation, you increase rainfall. And you may increase the river flow. This is a feedback. Feedback means a return effect. The human impact, rather than being considered as an external to the model, is part of the model because the human impact may affect the model itself. Feedback, it's a return effect. The feedback may be positive or negative. Positive is the case that I mentioned. I get water from irrigation, I reduce the flow into the river. But irrigation increases evaporation, which increases rainfall. Rainfall increases the flow into the river. This is a positive feedback. It's a compensation effect. Sometimes the feedback can be negative. The feedbacks are more important, are very important, and therefore one may say the second category is preferable. It's preferable if I consider humans as part of the system. What is the downside? The downside, the negative part, is that the model becomes more complicated because you have to include, in my example, a model of effect of evaporation, increased evaporation on rainfall. It becomes more complicated. Also, keep into account that humans are less predictable than nature. And therefore, sometimes it may be better that we just include the human impact as something given, not something developing. Because, as I said, humans are less predictable than nature. We are almost done with this. What I would like to do is just to discuss a little bit about uncertainty assessment, but very limited. And then, again, if we have time, I would like to make an exercise. Just a few words. I will tell you something on the bus, on the place that we are going to visit on Thursday. For those of you who came a bit late today, just two quick reminders. 8:15, the meeting point for the field trip. The weather should be better than today. In any case, please keep an umbrella. If you see that the forecast of the weather is, take an umbrella. If you see that the forecast of the weather is not very good, and your shoes, we are going a walk over a field, and therefore there is grass, there is, and if it just rained, you know, the grass is bad, and therefore keep appropriate, take appropriate shoes. And I think we will have a first part in a room if the weather is very bad. Otherwise, if the weather is fine, I think it will be fine. We will have to walk on the field for a while. Second reminder, on May 23rd, there is the surveys of your opinion on the official survey by the university on this course. And please make an effort to be here on that day. It is Thursday, May 23rd, because I need at least 10 people in the room. Today you are just 10, so I hope that there will be some more attending on the 23rd. Okay, and that's it. And about next week, I think. Please take your PC on Monday, okay? Because I would like to concentrate again on exercises. Thank you.